Hello and welcome to another lecture. Today we're talking about another type of partial differential equations, namely the wave equation. The equation is marginally different from the heat equation we considered before, but that difference has a profound effect on what we can observe in the solutions of this equation. Just as before, we're going to have an equation, boundary conditions, and initial conditions. The equation reads partial derivative of u with respect to t twice should be equal some constant c squared partial derivative of u with respect to x. X is limited to the interval 0 to L. T is just greater or equal than 0. We're going to consider three different types of boundary conditions imposed on this equation. We're going to consider a string that's fixed at both ends, so that for whatever time at x equals 0, the string is always at the position 0. And at the opposite end, we also have the string fixed. Another type of boundary condition is when the string is fixed on one end, but at another end, it's not fixed and free floating. So the partial derivative with respect to x is 0 instead of the function itself being 0. We can also have a free floating end at 0 and a fixed end at x equals L. So it's probably very intuitive to understand that if we set function u to be 0, then we're fixing the end. Why is it that when the end is not fixed? What do I mean by not fixed? We can think about a string being stretched between two positions, position x equals 0 and the position x equals L. So by fixing the position to be 0 in terms of the motion of the string means that we're fixing the end. At another end, we can attach the string to a tube that slides up and down on a rail. So we're fixing the position x equals L, but we're not fixing the upward and downward motion of this end of the string. So why does the derivative have to be 0? This can be explained this way. The string is always under tension, so there's always some kind of a tension force present. And if this sliding device has no friction, then there is no way that the sliding device can exert an upward or downward force. It can only exert a force parallel to the x-axis. So if the string is at the angle, that means that there is an upward force on this part of the string, which can't happen because this part of the string cannot exert a downward force, because we know from Newton's equations that every action produces equal but opposite reaction. So if we assume that string has no mass and that this apparatus right here has no mass, then there is no way that the string will be at an angle to this sliding tube. Yes, this is unphysical. Everything has mass in the physical world. And if this apparatus has any mass and exerts a gravitational force, then the string will have an angle to it. There's also the fact that the string is somewhat fixed to maintain the position x will prevent any whiplash effect. So the string will never curl, it will just be always a function of x. So I hope this little diagram will help you understand why the condition u sub x being 0 means that the end of the string is free floating. There will also be initial conditions, and since we have two time derivatives, there will be two initial conditions. U of x at time equals 0 will be some kind of function f of x, and time derivative at time equals 0 will be some kind of function g of x. We derived the heat equation in the previous sections, but I didn't derive the wave equation. It's because the derivation kind of complicated, and I would rather give you an intuitive understanding where this equation is coming from rather than give you the full derivation. We can understand the equation as Newton's law. The second order time derivative is the acceleration of a particle on a string at the position x. And second derivative with respect to x has a meaning of a curvature of the string. So the string will only accelerate. So if we think about several possible configurations of the string, so suppose I fix the string between 2 points and just leave it be, or if I have string fixed between 2 positions and it has some sort of a profile, then we can intuitively understand that because the string is under tension, this part of it will go down, this part of it will go up. However, as time progresses, the string will probably reach a position like that, but this part of it was going down and this part of it was going up. So the velocity will still be preserved and the particles in the string will continue to move in this direction. So what happens here is that the acceleration of each particle at each position depends on how much the string is bent. Because in this particular example, the string will stay where it is. It will not try to move, it will just continue to be the straight line that is a stable state of the string. So the derivative in terms of x does not affect the motion of the string. The fact that the second derivative is 0 does not mean that the speed is 0. This gives us the intuition that the second derivative has something to do with acceleration, and the first derivative should not affect the motion at all. And this is what this equation exactly does. It ties the acceleration of a particle to the second derivative in terms of x. So if the string is bent, the particles will accelerate. If the string stays in a straight line, the particles will not accelerate and will either stay at the same position with a 0 velocity or will continue moving with a constant velocity. And we're going to observe those effects in the solutions, and we're also going to observe those effects in real-world experiments with strings. So just as before, we're going to use the method of separation of variables. And in that method, we assumed that the solution u of xt is a summation of Cn times u sub n of xt, where each u sub n of xt is sort of a building block solution that has a form product of a function that just depends on x and a function just depends on t. We also assume that each function u sub n satisfies the differential equation with boundary conditions. So u sub n differentiated twice with respect to t should be equal to u sub n differentiated twice with respect to x. And given one or the other type of the boundary conditions, the function u sub n should satisfy it. So either u sub n at 0t equals 0 at both ends, or u sub n x at x equals 0 but u sub n at another end being equal 0, or it's fixed at the 0 end and free floating at the opposite end. So if I plug in x of x times t of t in the differential equation, then I'll get this. Partial derivative with respect to time is only going to differentiate t of t. So x of x times t double prime of t should be equal c squared times x double prime of x times t of t. Dividing by x of x and t of t, I get the following. I'll also move c squared together with t's. And here we arrive to familiar looking equations. And remember last time when we considered heat equation, we made the conclusion that both of those fractions have to be constant. The same logic applies here. On the left we have a function that depends only on time, and it cannot depend on x. On the right hand we have a function that depends only on x, which cannot depend on time. So therefore both of the fractions cannot depend on x and cannot depend on time. And just as before, I'm going to denote the constant as minus sigma. So this gives rise to ordinary differential equations. We have an equation for x, and we have boundary conditions. I'm not going to write them out because we're going to consider each boundary condition separately. And we have a similar equation for t. And we're only going to impose the initial conditions when we assemble the solution together. So let's consider the first type of boundary conditions when I have a string that has both of its ends fixed. So if u sub n of 0 t equals 0, that means that x of 0 times t of t should be 0. The same can be said at the end L, means that x of L times t of t should be 0. Which means that if we want to have non-zero solutions, we should let t of t to be a non-zero function. And therefore x of 0 and x of L should be both 0. We entered the boundary value problem in the case of heat equation when x double prime plus sigma x was 0 and x of 0 and x of L both were required to be 0. We arrived to the conclusion that in order to have non-zero solutions, we must have sigma being equal pi n over L squared and x of x being sine of pi n over L x. This time the equation for t has second order, therefore we have to solve it from scratch. We get that t double prime plus c squared times pi n over L squared times t should be 0. This is a differential equation that we know how to solve, and the solutions are some constant times cosine of pi n c over L t plus another constant times sine pi n c over L t. Therefore my building blocks will be product of these functions. And the full solution is the summation. I'm letting n to be from 1 to infinity because I do know that sigma cannot be 0, because in this case there will be no non-zero solutions. So n has to stay positive. N being negative only flips the sign on the sign, therefore just negate the constants an and bn. Therefore n has to be positive, and that means that n would go from 1 to infinity. So all I have to do is to add up all of these functions. So how do we determine coefficients an and bn? Well, remember we had two initial values. So we also knew that u of x0 should be equal to f of x. Well, if I plug in time equals 0 into my expression, I'll get that it is a sum as n goes from 1 to infinity, an times cosine of 0 plus bn times sine of 0 times sine of pi n over L x. Since cosine of 0 is 1 and sine of 0 is 0, this just becomes the summation as n goes from 1 to infinity of an times sine of pi n over L x. So an are just the coefficients of the sine series of f of x. So that means it's t over L, the integral from 0 to L of f of x times sine pi n over L x dx. We also had the second initial condition that the time derivative at time t equals 0 was g of x. And that should be equal to the sum as n goes from 1 to infinity. We have an times minus pi n c over L times sine of 0 plus bn times pi n c over L times cosine of 0, all multiplied by sine pi n over L x. So what happens here is just a summation as n goes from 1 to infinity of bn times pi n c over L times sine of pi n over L x. So again, it is a sine series, but there is a coefficient in front. Therefore, each bn has to be computed as t over L times L over pi n c times the integral from 0 to L of g of x times sine of pi n over L times x dx. So once we computed the coefficients an and bn, we add the series together and get the solution to the problem. So let's consider a simple problem. We have c being 1/2. We don't have a function g of t, so the coefficients bn are all going to be 0. We do have a function f of x given to us, so therefore we have non-zero coefficients an. So coefficients are going to be t over L, and L here is 3. The integral from 0 to 3 of x times 3 minus x times sine of pi n x over 3 dx. And then u of xt is going to be the summation as n goes from 1 to infinity of an times cosine of pi n times 1/2 t over L, which is 3, times sine of pi n x over 3. Again, I don't want to compute the coefficients an by hand. We can use mathematics instead. So here's the setup. L is 3, there's my f of x, g of x is 0, c is 1/2. Each coefficient ak is computed as sine series expansion of f of x. Each coefficient bk is computed as a sine series expansion for g of x, except that the coefficient in front is, instead of t over L, it's t over pi kc. enumeration is going with respect to k, which is just a change of the name, so it's really not that big of a deal. Then I add up my series and I create a function that is just this series. And later on I plot the function. So here's the plot of the function f of x. This is the initial state of this string. Let's add all of that up and observe the vibrations of the string. So the string does something weird. It kind of flattens out and then again curves up, and it keeps doing that. If I let time to go from 0 to 100, I'll see how my string vibrates, and it's going to go forever because this equation does not model any sort of energy loss through friction with air or heating up of the string due to constant oscillating deformation of the string. All of those effects need to be properly modeled before we see the picture that is physically accurate. The introduction of damping can be easily achieved by introducing u sub t component in our equation. However, it will make the solving this equation a little bit more complicated. For purposes of clarity, we assume there is no energy loss in that system. I also prepared a few other functions that are kind of interesting. One of them is the step function. So what if my initial configuration of the string is slightly different? What if it's just a function that is 0 up to 1, then jumps to 1, then jumps back to 0 at 2? So let's see what happens. Let me redefine. We have now some sort of a going back and forth waves. And that's how this string vibrates. Is this physical? Let's add up a little bit more terms. See what happens. So the behavior of the string is very weird. The waves are going back and forth, then they add up and subtract each other. And you wouldn't assume that this will be the behavior of the string. The vibrations of the string later on deteriorate into just sinusoidal vibrations, and that doesn't happen here. That is the consequence of the fact that there is no energy loss. And if you film the string with a high-speed camera, you will see these kind of effects. So let me show you another interesting function. This is where we plug this string, but we don't plug it in the middle, we plug it in the position about 1/3 of the way. So we just stretch the string and then let it go. So this is the initial position of the string. Now let's see what happens as time progresses. We see this kind of effect that the string flattens out and then keeps reflecting itself. And there's this kind of a traveling flat wave phenomenon. Is this physical? And the answer is, it is. In the schedule, I give you a couple links to a few interesting YouTube videos, and one of them does exactly what we just modeled. The experimenter just plucks the string and then lets it go. See what happens. If you play the video, you can see this traveling phenomena. And then, due to damping, high-frequency oscillations die out. Go ahead, check this video out, it's very useful. Another video looks at a few phenomena that we can observe with wave-like systems when they travel back and forth. Or when the waves travel towards each other and add up. Will our equation have this behavior? Well, to look at this, I've created yet another function. This function has a width parameter which specifies the width of this little bump that I introduce in my string. So if I start with a little bump, then this is what happens with my waves. You can see exactly the phenomenon that we just observed in the real world, that the big wave splits into two smaller waves, travels towards the end where it gets reflected and flipped around the axis. Then they travel back towards each other, add up to a perfect copy, perfect reflection of the big wave they started with, and then the cycle continues. Okay, let's see what happens if instead of having f being non-zero, we'll have f being 0, but now specify the derivative. So f of x is now 0, but g of x is not. So initially we have a derivative. So you see, if this is specified derivative, the effect is very different. Let's go back to g of x being 0 and talk about strings that being plucked and then left alone. What I want to look at this time is the fact that this traveling wave is a summation of stationary waves. So let's look at the first component of my sum. It's just the string oscillating around the center. Just goes up and down, up and down, up and down. What's the second component? The second component is 0 because the coefficient is 0. Let's look at the third component. The third component is the wave that starts this way, but then it's a stationary wave. It doesn't move anywhere. It just goes up and down, up and down. The fifth component is also another so-called mode of oscillations. It's a stationary wave. It doesn't travel back and forth. It just goes up and down. It stays where it is. However, if I add these components, then I will see how the summation of these series creates a visual effect of a traveling wave. Can we see this mathematically? Absolutely. If you're curious, look up D'Alembert's solution of the wave equation, which is a mathematical trick that basically predicts with certainty that the traveling wave phenomena has to take place. So here, when I add the first 20 of those terms, the traveling wave phenomena starts to be very apparent. First 10, and it's really not that obvious. But again, every single component is just a stationary wave. Okay, let's look at a different problem. Now when we have one end fixed and another end open. Since these two conditions are symmetric, I'm going to derive the equations for only one of them. I'm going to assume that the left end is fixed and the right end is not. So this means that for the solution, u of 0t is 0, and also u sub x at lt is 0, which translates for every building block, u sub n of 0t should be 0, and u sub n x at lt should be 0, which will translate into x of 0 has to be 0, and x prime of 0 has to be 0. We knew what kind of solutions we get. We get that sigma will have to be 2n plus 1 pi over 2l squared. We also derived that each solution x of x has to be sine of 2n plus 1 pi over 2l x. And now we have to derive the expressions for the function t of t. The equation for the function t of t reads t double prime plus c squared times 2n plus 1 pi over 2l squared times t of t should be 0. This leads to the solutions t of t having to be a sub n cosine of 2n plus 1 over 2l times c pi t plus bn sine of 2n plus 1 over 2l times c pi t. So therefore, the full solution must be the summation n goes from 0 to infinity, because for the quarter period series n has to start at 0. We have a sub n cosine of 2n plus 1 over 2l c pi t plus bn sine of 2n plus 1 over 2l c pi t multiplied by sine of 2n plus 1 over 2l times pi x. And the coefficients an and bn are computed just as before. An will have to be now a quarter period sine expansion of the function f of x. So it's 2 over l integral from 0 to l of f of x times sine of 2n plus 1 over 2l times pi x dx, and the coefficient bn 2 over l multiplied by 2l over 2n plus 1 times c times pi, the integral from 0 to l of g of x times sine 2n plus 1 over 2l times pi x dx. So here we have a simple problem. We have one end fixed. The end at x equals 3 is free floating. We have initial conditions. Solution u of xt will be the summation. Again, the coefficients bn are all going to be 0 because the g function is 0. So we'll start summing from n equals 0 to infinity. Coefficients an times cosine of 2n plus 1 over 2l times pi, c is 1/2, times sine of 2n plus 1 over 2l, which is 3, so both of those are going to be divided by 6, times pi x, where an is computed as 2 over l, so 2 over 3, the integral from 0 to 3 of the function x times 3 minus x times sine of 2n plus 1 over 6 times pi x dx. So the second setup is very similar. We're computing quarter period series now. Instead of just sine series, we add them up, we define the function u, and then we plot them. You can see the telltale sign that the other end is fixed. We have a 0 derivative over there. If I let t slowly move, we can see that the oscillations are a lot different than the oscillations we observed in the first case. So this is the consequence of the other end being completely free to slide up and down Let's try all other functions that we have. So let's try a string that was plucked and then released. So here's our plucked string. Let's see what happens as time progresses. We see again this kind of a traveling wave phenomenon going on, and the other end of the string seems to be completely flat. This doesn't look very physical, but again, in this model we don't consider any energy loss due to damping, and that's why we see it there. If you try to record the actual string in slow motion that has this kind of a setup, you will see exactly the same motion for the first few seconds of it. Let's see if the traveling wave phenomenon is still there. If we let the time to progress, this is what we see. We see the waves splitting into two, but then at the left end, the wave is going to flip around because it's going to be reflected and flipped. Watch what happens at the right end. Just being reflected backwards. And now they will cancel each other out. And then they go and travel on their own. So the fixed end reflects the wave and flips it. The non-fixed end doesn't reflect it. It reflects the wave, but it doesn't flip it. Let's watch that again. We have the waves traveling, and then the right end we have the wave reflected but not flipped, and the left end we have the wave reflected but flipped. Both of these phenomena are observed in the real world. Go ahead and watch the videos that I linked in the schedule. They're quite interesting. I want to warn you, the second video has a terrible background noise, so you might want to turn the volume down for the second video. Alright, this is how you solve the wave equation. Again, we applied the method of the separation of variables. It worked fine for this type of equations. The series are a little bit more complicated. There's more coefficients to consider. There's also a second initial condition to consider. So it's a little bit more complicated in terms of how much computation you need to do, but conceptually it's exactly the same. Exactly just in the previous case, we started with the assumption that the function u sub n is a product of two functions x of x and t of t. As I explained before, this assumption may not be true under certain conditions, but for the simple cases we consider today, it is true. And then we derive two ordinary differential equations that have only one variable present in them, and we're solving them using the standard method you learned in your differential equations classes. We saw that the fixed end lead to the sine series expansion of both functions f of x and g of x, and when one end is open, it leads to quarter period expansion. We considered the case when the right end is open, and that led to the quarter period sine series. If we consider the case when the left end is open and the right end is fixed, then the only change will be here is the x of x will be the cosine rather than sine. I hope you enjoyed the lecture. That's it for today, and I'll see you in our next video.